Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 1st, 2025, which was about 2 days ago. The headline result is a plug-and-play compressor for code that achieves up to a 5.6 times reduction in context without hurting task performance. The paper is titled LongCodeZip Compress Long Context for Code Language Models. And as we'll see later, the efficiency gains are striking. In short, the method uses a two-stage, Perplexity-guided selection over functions and blocks, improving code completion, summarization, and question answering while cutting prompt tokens by about 77%. Also, the authors shared the official LongCodeZip implementation on GitHub. You'll find code for 3 tasks: repo QA, long code completion, and module summarization, with main scripts, a core code compressor module, and run.sh for quick experiments. It includes installation steps, configurable compression ratios and token budgets, model selection, and multi-GPU support. Well, Figure 1 contrasts surface similarity with true dependency signals in long code contexts. The left panel shows a case where lexical overlap makes retrieval succeed because the helper function closely matches the target. The right panel shows a dependency case where a configuration class matters, yet similarity ranks it low. An approximated mutual information score, which measures how much a snippet reduces uncertainty about the instruction, correctly elevates the configuration code. Alright, Figure 2 shows the LongCodeZip pipeline that compresses long code by choosing snippets which most reduce the model's uncertainty about the instruction. Approximated mutual information means we score a snippet by how much it lowers perplexity when predicting the instruction. On the left, coarse-grained compression ranks functions and keeps only the most relevant ones under a budget. On the right, fine-grained compression splits each kept function into blocks and selects the highest scoring blocks to meet the token limit. So, Table 2 shows long code completion results, highlighting that compression can stay accurate while cutting context. Edit similarity, which measures partial correctness by the fewest edits needed, reaches about 57.6 for Q1 2.5 Coder 7b. Exact match is around 32.4 for the same model. The compression ratio is about 4.3 times, which reduces cost because only the most informative blocks are kept. On Coder 8b, the ratio climbs to roughly 5.6 times. So, Table 7 reports an ablation study that shows which components drive gains. An ablation study means the authors remove or swap parts of the method to measure impact. Coarse ranking with conditional perplexity is pivotal, since replacing it with similarity drops edit similarity by about 7.9. Random ranking hurts far more, cutting edit similarity by about 17.8. Fine-grained pieces add steady value, because removing them costs about 1.5 on edit similarity, while adaptive budgeting recovers roughly 2.3. The full LongCodeZip configuration reaches about 57.6 edit similarity at roughly 4.3 times compression. Wrapping up, 2 takeaways stand out. A simple 2-stage, perplexity-guided compressor that selects the right functions and blocks, and real wins at scale, with up to 5.6 times compression, big latency drops, and no meaningful accuracy loss. The implication is cheaper, faster long context coding for many models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.